Party started. So charging systems will finish up kind of the three amigos, three musketeers, if you will, of battery starting charging. Keep in mind the whole time, they go together. So if you have a problem with the battery, consider the starting and the charging system. If you have a problem with the starting system, consider it could be the battery. Maybe the battery's dead, but if the battery's dead, maybe it's dead because it didn't charge, right? And then if you have a problem with the charging system, generally the starting system won't cause that, but your charging system is going to function differently whether you have a good battery or bad battery, if that makes sense. If your battery is totally dead, it has no surface area on the plates, so therefore it has no cold cranking amps and no reserve capacity. Your alternator is going to be working pretty much as hard as it possibly can all the time. So does that sound like a good thing for your alternator? Right, not really, right. So when your battery's good, your alternator has to really pull the weight of the system. But in the event that you have lower electrical loads, your alternator can kind of back off and your battery can fill in the little where it's a little low, or if it's a little high, your battery absorbs it. If your battery's out of the picture, you're running raw off the alternator, that can be a little hard on it. Now, some people will take that a little bit too far, and alternators fail. Okay, we're going to look at some of the pictures and things that fail. Alternators can die like a natural death, or it could be kind of, maybe partially caused by a dead battery, but some people take it so far as to say, if your alternator is bad, your battery's bad, and that's not really true. So we'll know that they go together, but let's keep them separate. If you wanted to test a battery, you do a battery test. And if the battery tests bad, and you happen to also have a defective alternator, maybe you'd make that connection. Hey, maybe the bad battery overworked the alternator. But if you don't test the battery, you don't really know whether the battery is good or bad. So let's do the tests on each one of the systems, okay? So when we jump in here, I think you guys will find it's fairly straightforward. So let's go back in time. Old cars, 1960s. Everybody likes those 1960s vehicles. They have nice curves, and they have a lot of character, and they have sounds that you like and things. Those had very minimal electrical components. So they might have manual windows. They may have very minimal, not that bright lights. They may have no heated seats, all these things. So if you think of the older cars, we had more of a basic alternator. It would have to produce less. So typically our alternator output is measured in amps. So the electrical engineers for automotive will do a calculation. How many amps does the alternator need to be able to put out at maximum to meet all the loads? So if we jump to a newer vehicle, let's say a 1-year-old car that's got heated seats, heated steering wheel, power windows, power locks, power mirrors, massive amounts of lighting inside and outside, and a big audio system and all these types of things, you can quickly see there's going to be a lot more demand for electricity, right? So older vehicles had more basic alternators. Some of them had a separate regulator rectifier. Now, typically, they're built all in one. So this one actually is an older style. This one is actually a newer style. However, the thing that makes it newer isn't just how it looks, but if you do look at it, it would appear this one has a lot more ventilation. It would appear this one's a little more closed up. The output has all to do with the number of windings and how much of a magnetic field it can produce. And then we can get into even more, a more modern charging system on, let's say, a hybrid is going to be not an alternator at all. This takes a belt to turn. If you got a hybrid vehicle with that big high voltage battery, we can actually simply run that. Let's say that high voltage battery is 240 volts. We can take that 240 DC, run it to a DC generator, and we can make it charge at 13 point something volts, right? So we'll do different things depending on how new the car is. I've even seen some that have dual alternators. Also seen some that have, like some of the German cars will have a liquid cooled alternator. So, when we start to get these really big electrical loads, we have to start to get a little bit creative. These are all air cooled, but the more power you make, the more heat you're going to make. So if we start running coolant to these, that's like a $1,200 alternator. It seems kind of dumb, but that's how the engineers were managing the heat, right? And so we don't ever want to overcharge though, because if we just establish what this is and what it isn't, this generates electricity, right? But it's not for free. Like nothing's really for free. Even free tuition is costing somebody some money somewhere. It may be free to you. It's not free. This is not free either. So anytime we spin this pulley right here and we have this alternator activated, it's going to make a magnetic field, and the output is going to be electricity coming off of this terminal. So it's generating electricity. It's really technically a generator. Where's the energy coming from to generate the electricity, though? Think about that. Well, if this was connected to a big fan blade and you put it up in the air and the wind turned it, you're taking wind energy to make electricity, right? Wind turbine. If you took this thing and you shoved it at the bottom of a waterfall and the water landing on it made it spin, that would be like hydroelectric power, right? Makes sense? But we're taking something and making it into electricity. We're taking wind energy, making it into electricity. We're taking water and gravity energy, potential energy, and making it electricity. So in the car, where does the energy come from to spin this pulley? Exactly. Your engine's running, it's spinning a belt, the belt is spinning the alternator. So the more we field the alternator, that means make its magnetic field stronger, the more resistance there's going to be, the more power it's going to take to turn it. Make sense? And the power in your engine ultimately comes from, you think you know? I'll give you a clue. You had to pump it in there to make it go-go. The go-go juice. The more that alternator has to work, the more gas you're going to use, more fuel you're going to burn. Diesel, gas, CNG, whatever. The more fuel that vehicle is going to have to consume. So if our alternator charges at maximum rates all the time, don't you think it's going to consume more fuel? So everybody knows, like, oh, turn the air conditioner off so you save gas, right? But technically, you turn down the radio, you could save some gas because it's not going to pull as much electricity to make your speakers boom, boom. What number? I don't know. I don't do the calculations. I'm just saying technically. And also logically, if it's going to be using more fuel, that's going to affect our emissions, right? So newer cars are a lot different than older cars because they're more focused on the fuel economy and the emissions. So on the old cars, we had an alternator that would basically just run. On a newer car with an alternator like this, we're going to have the ECM, so the engine control module, or the PCM powertrain control module, is going to control this. Does that make sense? So it's going to look at the voltage of the system, and it's going to fine tune how strong the magnetic field should be so that it charges enough, but not too much. And that's, makes it a little more difficult to diagnose a bad charging system because now you have the computer controlling the alternator, whereas before you didn't. The alternator just did its thing with just like one wire going to it. The big cable and one small wire. All right, very good. So here's what it looks like. As you guys can see, it's just what I was showing you. The function, again, take mechanical movement from the belt, transfer that into electrical energy, charge the battery, run the things, power your lights, power your windows, power your ignition system that you need for the engine to keep running, right? That's its job. Here's a little overview of the components, right? So within that alternator, we'll come back to that. The alternator is going to charge the battery, but it gets a little tricky here because the alternator, when we call it an alternator, truly it's alternating current. So that's AC, in other words. But the battery is DC, direct current. So we have to have not only like a generator, an alternating current generator, alternator, we have to convert that to DC to actually work with the battery. And all of your systems in the vehicle are DC based. Right now, we may have some AC things. So, like, um, if you have, um, sometimes speakers could be AC, sometimes alternating current. If you had an inverter in the vehicle to power to give you a little spot to charge your laptop or something like that, that could be AC, but really the whole vehicle is DC. Everything's DC. So when we have an alternator that makes AC, we have to regulate the voltage, but we also have to rectify it into DC. When we change it from AC to DC, that's called rectification, which I'm going to show you. So in the alternator, we have this on the back side, we got this voltage regulator and a rectifier bridge. So the cool thing with the modern alternator, it's all in one. So we have two options right now. We could focus on it all as one, and you could just be like, very simple understanding of the alternator. But I don't think that's really the way to go. I think you should understand the AC side and how it goes to the DC side, mainly because you don't really have a good understanding unless you have the whole understanding, right? But the little bit of an argument against understanding it thoroughly would be, well, who cares if the problem's on the AC side or it's in the regulator or the rectifier? It doesn't matter because we buy an alternator as a whole, right? So kind of similar to the starter. We don't care if it's the starter motor or the starter solenoid because they come together, right? It's the same with this. Today, when you buy an alternator at O'Reilly's, they sell you the whole thing. But I still want you to kind of know the difference, right? So we're gonna talk about these as separate components. And actually, you know that you can go in and you can buy this regulator rectifier and you could actually change it really cheap. So it'd be good to have that one in your back pocket. And then other parts of the system, of course, the battery, like we discussed. But additionally, what do we have here? What's that battery light? Is that the Lego light? So if a customer comes in, they say, my Lego light's on. There is no Lego light. They're probably talking about the battery light, which is more appropriately called the charge indicator. So when people see the battery light on, sometimes they're like, oh, it must need a battery. But generally, a battery can't really cause a charge indicator light. So let me give you the down and dirty on how the charge indicator light works. You ever notice if you get in the car and you turn the key on, the battery light will come on, the charge indicator will come on. It will. You just get it. Don't start it. Just do click, click. Or if it's a push button, press and hold, or sometimes press twice without pressing the brake or something. Get it to be ignition on, get all the computers awake, get everything up and working, but don't start the engine. You will notice that the battery light will be on. What that's telling you is you have a voltage under some specification. So if this battery is fully charged, what's the number? You guys remember? 12.6 would be fully charged. 12.6 will give you the charge indicator. That'll give you the battery light. For that battery light to turn off, I'm going to give you a number, and this is a number for an example. Every car could be slightly different. 13 volts. If your system shows 13 volts, this indicator will turn off. How in the world is this 12.6 volt battery going to generate 13 volts to turn off the charge indicator? Yeah, exactly. The battery doesn't do the job. The alternator does the job. So while that light looks like a battery light, it's really more, is my alternator charging light or not? If the light's on, as a general statement, if the light's on, your alternator is not charging. Now, technically, your alternator could be charging and you may have a massive voltage drop on the charging cable, which will, take your 14 volts from your alternator. And if it's got a 2-volt drop, it may drop it to 12, right? So when I'm saying that it's not charging, I don't exactly mean the alternator is bad. I mean, there's a failure in the charging system. So you're not getting at least 13 volts if that light is on. So everybody understand what the battery light really is now? The battery light is saying your system voltage is below 13 or thereabouts, depending on the vehicle. Cool. So that'll be very critical as we get a little further. All right. And I think overall you're going to understand this. Alternators produce electricity by relative movement of magnetic field through a winding of conductors. So what I was saying is like this thing has to spin. The belt spins it. So there's relative movement between conductors and magnetic field. So if you're following what I'm saying, we have two different things here. As we get further into it, I generally like to call those the stator and the rotor. Sometimes we can call them slightly different things. The reason I like stator and rotor is because stator is stationary and rotor rotates. So I mostly use stator and rotor. So the magnetic field is created by the rotor, see, which rotates within the stationary motor windings. So the rotor rotates, the stator is stationary. So if we were to break this alternator down, you'd have some stuff on the outside, that's the stator, and some stuff on the inside, that's the rotor. And those two have they have a relationship, we'll just say. Cool, make sense? And then keep in mind, alternator converts mechanical energy into electrical energy by applying the principle of electromagnetic induction. All right, now it gets a little complicated. So we all understand this thing spins the rotor, the stator stays stationary. What that's saying right now, it's going to convert mechanical energy, that's your belt, into electrical energy using electromagnetic induction. So for electromagnetic induction to occur, we have to have magnetism, right? So right now, this spins really easy because the electromagnets are not activated. Make sense? If we activate the electromagnets, they start to build a stronger magnetic field, right? And then this becomes very hard to turn. You want to know the cool thing about making the magnetic field strong and this becoming hard to turn? The output will be more. So if you have a weak magnetic field, it doesn't generate a lot of electricity. If you have a strong magnetic field, it generates a lot of electricity, right? So now you can kind of understand we're going to vary the magnetic field and specifically applied to a new car, the ECM is going to control that. The ECM is going to say, we need more power. Increase the magnetic field, make the magnetic field stronger. Then your engine's actually going to have more load on it. Makes sense? Your engine's going to have a little bit more drag because it's having to turn that rotor through a very strong magnetic field, if you're picking up what I'm putting down. Right, and so we got a couple pictures coming up. This is the explanation that we're talking about. And this is the simplified version. We're only going to have a couple windings here. So if you look at this rotating part, it's a magnet, right? You see the south and north, there's your magnet. When this rotates, this coil right here is going to make a magnetic field. When this magnet rotates by that magnetic field, it's going to actually induce electricity into this coil, and this current is going to flow and, for example, light the light bulb. Make sense? Then when we get a little bit further, if you notice when they're right next to each other, it doesn't produce much. Then when we get a little bit further and they're back at 90s, it's inducing again. But what changed? Can you tell the difference between here and here? It went the other way. Yeah, exactly. It went the other way. So see, that's alternating current. It's alternating. It's this. It's not all the same direction, right? So if you notice, this south and north didn't change though, but we flipped the polarity on the electromagnets. So this is actually kind of similar to how the motor works, except in the motor, we're basically driving. We're using these and we're driving the rotor. But in an alternator, we're actually, basically the rotor is being driven by an external force, and we're just varying the amount of magnetic field to resist it. And the more we resist it, the more induction occurs and the more electrons will end up in this wire, right? But it is going to go to the left and then to the right. and to the left and to the right. Right, so if you kind of picture those, go ahead. Well, there could be different ways. I mean, if you picture like a motor, they could do it through commutation. They could do it electronically. So like if you get into something really new, let's say hybrid, for example, we can use IGBTs, insulated gate bipolar transistors, to switch the north-south, north-south, north-south. Or if it's older style, we'll send our electricity in and have it go through like a slip ring and brush, or, remember that commutator that was switching polarity in motors? We'll do something more like that, more mechanical. So if we were to take this apart, we would, in fact, I'd kind of be interested in that. We may do some of that a little bit later and try to look and see like, how is it switching? But generally in an alternator, the rotor is just a solid magnet and the stator does all the switching. One of the two has to switch. It makes sense in the alternator for the stator to do the switching. Cool. So if you just follow me like loosely, we got to switch these coils back and forth. And we're also going to change the amount of current flow, because with electromagnetism, the more current flow we send through here, the stronger the magnetic field will be. So if we just do a little bit of current flow, we could have it be like a light magnetic field, which will induce some, or we can induce more. And we got some more pictures and videos that I think will help. Right, so if you keep in mind, as the magnet rotates, the position of the poles reverse. So that's what your question was. The polarity of the voltage reverses as well. And so the direction of the current flow also changes. Who's playing their jams? I hear a little funky beat there. All right, so if we're flipping the polarity of the magnets, keep in mind that's how we're going to make our AC, right? I got a couple more diagrams that I think will help. So if we look down here, series of 6 diodes. What do diodes do? We covered that like in the first couple weeks. What's the purpose of a diode? Yeah. Yeah, so if we think about it, if the diode is a one-way valve, we can allow electrons to go one way, but not the other way. And if we arrange them with 6 different diodes, and we have basically 3 different circuits producing AC, we can essentially change that AC into DC, right? So that one's going to take a little bit more explanation, but just understand we're going to use diodes called the rectifier assembly. Remember I told you what rectification does. Rectifying is when we take the electricity from AC and we make it into DC. So if you were to think about it like erect a building, this would be how you stand the building up. We're going to take that AC that goes positive, negative, and we're going to rectify it into only DC. DC no longer goes back to negative, positive, negative. It's just going to go positive. Cool. So I'll show you that in a diagram. That one's pretty interesting. But what does that job? That's the rectifier. So if we have an alternator that the motor, the generator part of the alternator works, the magnets and the coils, all that works, but we have a bad rectifier, it won't make DC. If we were to have a rectifier with a bad diode, generally, you know what that would mean? Some AC in a way. AC would be output. So you could have AC current being output by your alternator, which can mess with some of the electronics, can throw some readings off and things. So one of the things we do when we do this test is we test for AC. If we have a good rectifier, we should have all DC. If we have a rectifier with a bad diode, we're going to get some AC. They'll call that like diode ripple. So if you hear this term, oh, we're going to check diode ripple, you're like, what? All we're saying is we're going to check the output of the alternator for being all DC. And if we have some AC, that would indicate a problem with the diodes. Fair enough? Pretty simple. Here's the thing though. If you have a bad diode, you're going to go to O'Reilly's, you're going to put an alternator on it. But to really understand it, you could be like, oh, it's a bad diode. That's in this regulator rectifier assembly. Technically, you could change that if you wanted to. Cool. So we got a couple diagrams that are really going to make sense about that. So just remember, the quantity of voltage potential induced by AC generator depends on strength of the magnetic field, which on a newer one, we control that with the PCM or the ECM. On an older one, that tends to more be with the voltage regulator. Also, the speed at which the magnet rotates. So think about that. Do you think your alternator is going to put out maximum at idle? Or do you think it might put out more if you're at 2000 RPMs? Yeah, that's for sure. That's why when we go to do a charging system test, a lot of times it has us rev it to a specified amount, right? So your alternator is going to put out probably pretty good at idle, but to really test it for its maximum, if you have a 100 amp alternator, it's not going to make 100 at idle. It may make 100 amps at 2000 RPM. So when we do this charging system test, that's why it tells you to rev it because, well, right here, the speed at which the magnet rotates, that's engine RPM. The speed at which the magnet rotates, that'd be the belt. So we got rev it. Cool. Then the relative distance between the magnet and conductors and the number of turns of wire on the stationary coil. So we don't change those two. That's in the alternator's design. So the electrical engineers figure out, how many windings and the distance. And then for us, we're just really testing the alternator to see if it outputs. And if it doesn't output correctly, it's probably not these two, because how could that change over time? But if the strength of the magnetic field is diminished because we're not able to field it correctly or something, that would change the output, right? So generally in automotive, we're going to have 3 to 4 coils of wire. So when we look back at this one, this is really just, we would consider this more like one coil. We're going to do this 3 to 4 times. So that way, remember how this one was making current to the left? And then when we got a little further and it's at a 90, that's no current flow. Well, that's not ideal, right? Like you get some current flow, then you got to take a break, and then you get some, then you got to take a break. Well, during this time, our battery would be discharging, and we'd also probably get a pretty big voltage fluctuation. You get like a high voltage and then a low and then a high, right? So we're going to do this 3 or 4 times so that there's much less of a gap between production. Kind of makes sense. That's what that one's talking about. And then when we talk about the phases, this is where it can get a little, some people, I've had a couple of debates with some people, and I told them, to really understand the alternator, they need to understand 3-phase. And they're like, no, don't teach them 3-phase electricity. But I don't really think it's that complicated. So I think you guys will be able to follow. Right here, this is AC, right? Alternating current. If we look, it went positive, then negative, but it didn't just go positive, negative. What it really did was it went from peak positive, lost a little, 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 went to 0, but then it gained a little negative, gained a little negative, gained a little negative, and then it reached its max negative, right? So if this was coming out of the wall, it would be pushing 120 and then pulling 120. And you would be, technically there's a cycle time, right? So it's not like switching from positive 120 to negative 120 instantly. It ramps back down and it ramps back up and it ramps back down. The number of ups and downs, so if we were to just go peak to peak, we would like out of the wall 60 hertz, which means 60 times per second. So it's really fast. If you were to plug your cell phone charger in, it's already designed to function on 120 volt AC at 60 hertz, right? So 60 times a second, it should switch back and forth. It's designed to take that power, work off that power, and charge your phone, charge whatever the appliance or the thing is that you plug into the wall. It's all set up for this, right? That's just AC. That's how AC works. However, if you were to go to Europe or something, they don't work off of 60 hertz. They work off of 50. So their cycles in Europe are going to be slower. Why? I don't exactly know. They came up with a different number, whatever. They figured out what they wanted to do. We could set it up for any number of hertz, any number of cycles per second. But what we came up with here is 60. So we're going to use our baseline of 60. Now, let me explain how that would be produced, right? How fast this goes up and down all has to do with the speed of the thing generating it. So if it was this, when this spins, it's going to generate the ups and the downs, right? But the faster it spins, the ups and downs are going to be a lot faster. They're going to be a lot closer together. Does it kind of make sense? So when you plug your microwave in to the grid, you're anticipating a generator somewhere producing 60 hertz. Okay, everybody good on hertz now? That's the cycles. So if you plug your appliance in, you're expecting 60 hertz. There's a generator that's literally spinning a certain exact RPM to produce 60 hertz. Now, if it's 59, it'll probably still work. If it's 61, it'll probably still work. But who remembers brownout? You've heard the term brownout? There's when the power goes out, right? But that's when everything is good and then boom, everything is dark. But if you ever had one where the lights look good and then all of a sudden they start to get kind of brown, your things start to slow down. Your microwave, when you're microwaving your hot pocket or whatever, it's like you hear it start to slow down. That's a brownout. That's when you're going from 60 hertz and that generator cranking that 60 hertz starts to slow down because it's overloaded. Everybody's running their AC. Everybody's microwaving their bagel bites or whatever it is that they're doing. If that generator can't keep up, it slows down. You get what I'm saying? So if we drop to like 42 hertz, it's because that generator's bogged out. That's when your lights go kind of brown, and that's when you can pretty much guarantee the power's getting cut. Any second, poof, it's gone. That's what a brownout is. Now, if you think about that, that's really the reason that AC works so well is because we got a generator spinning somewhere. Cool. However, in the alternator, we don't necessarily need 60 hertz. We can deal with whatever hertz this thing makes. We have the regulator and the rectifier that are going to make that into DC. That's going to be, work for the system, right? So we have however this RPM is, however fast this RPM is, that's going to make a certain number of cycles. And we're just going to basically take those cycles, make the best of it, rectify it, and then have it charge the battery. But if you have more RPMs and you're working with 120 cycles, that's going to be even, you can produce more power, put it back in the battery. So everybody's kind of good on this AC, right? Positives and negatives. This was produced, that peak right there was produced right here, right? This is a positive and it's right at its peak. Then when it turned 90, look what happened. No current flow. That would be down here, right? It was at its peak and then it was less, and then it was nothing. But then guess what happened? It kept turning and now it's getting more and more until it's at its peak. But it's at its other peak. It's at the negative peak. So this was more and more negative peak. Then it gets less, zero, more positive. Can you guys see how this AC would be produced by this thing spinning? But like I said, there'd be too much of a gap between the power pulses, right? So instead, how about we do this? We do that 3 times. Why do it 1 time? We could do it 3 times. So that would mean we'd have 3 magnets and 3 sets of those north-south coils. Get what I'm saying? What if you took this and you did it 3 times? You wouldn't have all 3 going at the same time though, because then you just have like a massive power pulse and then nothing at all. And then a massive one. So instead, you know what we do? We stagger the start times. You get what I'm saying? So if we stagger the start times, look, here's phase 1. Now, if you think of 360 is like you're snowboarding and you pull a 360, right? If you wanted to fit 3 pulses into that one 360, how many degrees apart should we space them? In other words, what's 360 divided by 3? It'd be 120. So if we space them out every 120, that'd be like, all right, pulse right here, spin 120, pulse right here, spin 120, pulse right here, spin 120, pulse right here again. Get what I'm saying? So if we start this one and then we wait 1/3 of the cycle, which is 120 degrees, and we start another one, then we wait 1/3 of the cycle, which is another 120 degrees, then we start another one. So we basically do one at 0, one at 120, one at 240, and then if you notice, it's back hitting 0 again, right? So all this complex thing is that looks like DNA or something is just one of these times 3. 1, 2, and 3, and they're spaced out by 1/3 or by 120. Kind of get what I'm saying? Exactly. Yeah. Exactly what it is. We did the same thing with motors. With a motor, you could have just one of these. This is actually basically the same artwork as the motor. If you did one of these, your motor would make a bunch of power, then no power, then a bunch of power. But instead, we'll take a motor and we'll do like, we might do more than 3 sets in a motor. We might do like 12 or 9 or some number, right? With this one, all we really did was we tripled the sets of magnets, tripled the coils, the field coils, and then set them off by 120 degrees. So now you have this one producing, but as soon as this one starts to fall off, phase 2 comes in strong. And as soon as phase 2 starts to fall off, phase 3 comes in strong. Then as soon as phase 3 starts to fall off, phase 1 is back. And 2 and 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And then typically if you get into, the hybrid EVs, we still use 3-phase. And so that's why I'm saying it's really critical that you understand at least this in concept, because when you work on a 3-phase motor, there's 3 wires and it says W, V, and Y. I think W, V, and Y. U, W, and V. U, W, and V. And you're like, what the heck is U, W, and V? Where's the ground? It doesn't need a ground. Because if you think about it, it's alternating current. Alternating current doesn't need a ground. Alternating current makes the positive and the negative. DC is funny. We're only positive, so we need a negative to actually draw the current. But if it's cycling positive, negative, it doesn't really, the ground's not relevant. So when you get into hybrid EV stuff and you're like, why has that motor got 3 wires going to it? Is there 2 positives and 1 ground, or is there 1 positive and 2 grounds? It doesn't work like that at all. It's got each phase is the positive and the negative depending on where it's at in its cycle. So there's always positives and there's always negatives. Pretty interesting. All right, so now look at this 3-phase. What if we were to use a diode and cut off the whole bottom half? And what if we were to use a regulator and we were to really just cut it off right here? You could see you're just going to have positive voltage, positive, 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 right? But there's still going to be a little bit of a pulse. So I don't know if you remember back when I talked about testing batteries. Remember I said one of my clues, if I go jump start a car and I go to pull it in, I'll look at the dome light and I'll see if it flickers. If the dome light flickers a little bit, what I'm actually seeing is the tops of these 3-phase coming out of the alternator, you can see a little bit of flicker, right? So if we were to wipe this out and just have this, that's a little bit of flicker. But if your battery's fully charged, your battery's going to stabilize that. Make sense? That's one of the functions of the battery. It doesn't have to be so raw, because when it's a little high, the battery absorbs the highs. When it's a little low, the battery fills in the little lows. It's a buffer in a sense. Right? Now, if we go from there, we can look at some of the parts. And then when we start to look at, the regulator rectifier, just remember the spinning magnet parts of the alternator, those are going to produce AC, and AC is not what we need. Cool. So here you go. We got the rotor. That's the spinning thing. You notice these are magnets. You've got the stator, and this stator is going to be wired into electrical control. So we can do switching things and whatnot. Right, so you can see that there. This would be probably inside here, right? This is just like a different angle, a different view. And this is a different view of the rotor. And then this is mostly part of the housing. But if you notice, it says a one-way clutch. This one, for example, does not have a one-way clutch. This one's just drive or not drive. This one, though, if I try to spin it backwards real quick, I can get the one-way clutch to slip. So this one has a one-way clutch. The main purpose of the one-way clutch is when you're running the vehicle and you shut it off, sometimes the engine, when you shut it off, will actually try to stop on a compression stroke and the compression will push it back down. So the engine will go forward, but then when you shut it down, it might go backwards a little bit. That tends to make the belt squeak. And so we threw a one-way clutch in there so that way when it tries to back up, it just freewheels the one-way clutch and we avoid a belt squeak. That's one of the main reasons we do that. Then if you look over here, we got the regulator rectifier. So in this case, we'll call it the rectifier and voltage regulator. This is the thing that is going to take that AC three-phase and convert it to DC and send it out. Makes sense? That's what does that. That's going to be 6 diodes in a bridge and some other electronic stuff. That generally needs some sort of a connection. So like on an older one, it would get just like a battery voltage connection. And that was enough to power the electronics and have it do, some regulating. But on a newer one, it's probably going to have several wires, but one of the wires is going to be from the computer to control the strength of the magnets to control the field. And it's going to basically make sure that it doesn't overcharge and it doesn't undercharge, right? So once it's computer controlled, this is also where the connection comes from. And that's something that gets a little bit more complex. And that's all the electrical stuff. However, has anyone ever had an alternator that's loud and noisy and whining or growling or grumbling? That could be bearings. Look, we got bearings here, got a bearing here. So if we have a bad bearing, it'll make noise, typically growling, and it's nothing really, you don't have to know anything about three-phase or the regulator rectifier. You have to be able to pull this apart and pull a bearing off of it and put a new bearing on it and put it back together, right? So some alternator failures won't cause a battery light. They'll just be a noise, at which point we'll use a stethoscope, we'll listen to it and be like, oh yeah, that alternator's noisy, it's got a bad bearing. That happens quite often. Whereas if we had a problem with the stator or the rotor, it may underproduce, which may give us the battery light and a low voltage. Or if we had a problem with the regulator rectifier, that could give us a battery light and a low voltage, right? So if the alternator is not charging, probably most of our work is going to occur rotor, stator, and probably even really, really more of it's going to be regulator rectifier. Okay, makes sense? Then, of course, you do have to consider if you had the one-way clutch and the one-way clutch was slipping all the time, or your belt was slipping, or your belt blew off 4 miles ago. If your belt's not spinning the rotor, it's not going to generate correctly, right? So that would be like in the visual inspection, you should be able to see that pretty quick. Cool. All right. And I think overall, you guys probably should be getting this. So we're going to be controlling the alternator's output by the amount of current flow that flows through the rotor's field coils. Okay. And then when we can get into the old school versus the new school just a bit, because we do have an old school car here that has the alternator separate, and then it has wires going to the regulator and rectifier, which is like a couple feet away. That's old school stuff. So that was kind of fun. They could be mounted in different spots, but pretty much anything new, they're going to be mounted together. To me, it makes most sense to have it mounted together. But on some of the older cars, it was literally an alternator hanging there, and it was, literally just putting out three-phase AC, and then we'd run the three-phase AC over to the regulator rectifier somewhere else. Then, of course, this was just a shot of the battery light, right? So if you see a battery light, that just means it's under 13 or so volts. then we got to start looking at, is it something with the alternator rotor or stator or regulator rectifier or the belt? But unfortunately, it gets a little bit more than that because we also need something here to control the electronics. So depending on what type it is, if we had this disconnected, it's not going to charge. Or if we had a mouse that chewed it, it's not going to charge. Or like where we're going with this right here, if it's computer controlled, the PCM is going to send basically like a duty cycle, an on-off signal. And so if it sends a duty cycle of 20% on, 80% off, that's only going to field these coils lightly. Whereas if we send 80% on, 20% off, that's going to field this more strongly, right? But if the wires that go to that part, which on this one, it's actually right here, it'd be this connector. If those wires are, it's actually this one. If those wires are damaged, it's not going to get the signal, right? So if we back out for a second, you say, vehicle's not charging. What's wrong? I could say, well, it could be the alternator. That's true. It's got the battery light on, could be the alternator. But if you understood what I just said, it could also be those wires coming from the PCM going to the alternator that could be open, chewed, high resistance, disconnected, right? So if it's an open in this harness and you replace the alternator, is it going to fix it? No. And then you'd be like, oh, I put a $300 alternator in and it didn't fix it. So that's where we want to dial this in and understand the PCM is going to send a duty cycle signal right here. And if it's not sending the correct signal or the correct signal is not making it there, this is not going to operate correctly. There's external things this needs to work. Kind of similar to the starter. If your starter relay is not sending a signal to that solenoid terminal, your starter is not going to work. You could put a new starter in there, but it's not going to work, right? So some of the goal of this is just learning and understanding what the alternator needs to do its job. Sadly, yes. So if you think about it, that PCM needs to generate a duty cycle to control the alternator, but it's going to use transistors inside. And if a transistor fails, it's not going to send any sort of a duty cycle pulse. It could be inside the chip of the PCM or the ECM or whatever controls the charging system. Yes. Which is really why when we get into the diagnosis, I want to make sure you're good to check the inputs so that you know if it's getting what it needs to work, right? It could be very simple. Go to the alternator. Is the belt on? Yes. Is that big positive terminal on and is it getting correct voltage? Yes. On the smaller wires from the ECM or PCM, what is that supposed to get? And I'm going to say it depends on the model. Like some of them are different. There's all sorts of different designs, but if we use the most common, it's going to get a duty cycle signal. You could use your meter, put your meter on duty cycle, probe it, and it's going to actually show you a percentage. If you have a percentage of 80% and the alternator is not working and it has those other things we checked, then the alternator is defective. But if you probe it and it shows 0%, you're like, is this getting the right signal or not getting the right signal? It's hard to say. And some manufacturers may default to sending 100% all the time, which means maybe it charges at maximum because it's not getting the right signal from the computer. Mm-hmm.
The alternator still doesn't give a problem, that means the alternator's bad?
Yeah. Yeah, because it's getting the signal that it needs to work. It's just not working. But if you were to check in and were to get 0%, I don't think the alternator is not going to charge if it's getting a 0% signal. So why is it getting a 0% signal? If a mouse chewed a wire, that's going to be 0% because the voltage is not going to make it there, right? And then you'd be like, oh, look at this rodent damage. Fix the wire, then all of a sudden, boom, it's up. Cool. All right, so in the interest of making sure we cover the right things, we'll over prepped on this one. Here's your rectifier. So this rectifier is how we change that AC to DC. This is what it physically looks like. Do you notice there's fins on it? Why do you think there's fins? If there were fins on a motorcycle engine, why do you think? There are fins on a Volkswagen Beetle engine. Bingo, air cooling. So these fins are on here to cool it down because when these diodes work to do rectification, it makes heat. We got to get rid of that heat. So we put fins on there. And then keep in mind, when our alternator's spinning, it's got little blades, like this one shows it really well. This belt is going to spin this pulley, which has fan blades in here, which is blowing cool underhood. It's kind of warm, but cooler than the electronics, engine air through the housing and through the regulator, rectifier, and all that. That's how we're cooling it. So that's how it physically looks. Here's how it electronically works. Remember, now we've got 3 different sets of coils. If we look at this, our rotor is spinning. It's going to go through the stator coil. Let's start with A. Current flow is going to come down here. Remember, in the 3-phase AC style that we became familiar with. So AC is going to come up through here. It's going to go to this diode. And this diode is going to allow positive this way. And then let's just say when it starts to go back around to the negative side, we're going to have no electricity going through the diode, right? Because the diode's one way, right? So if we have current pushing to the right, the diode allows it. But if we have current pulling to the left, what happens with that diode? It's going to block it because that's the job of the diode, right? So if you look at that, we're going to use this diode right here. And then what's interesting is we can actually pull through the negative side. Then when we go over to B, we're going to push through the positive side. That's going to go through diode B. But the positive side goes to the positive side of the battery. The negative side's kind of interesting. It goes to the ground. And then if we go to C, and this coil is spinning, this rotor is spinning, it's going to push positive through C, which is going to go through the positive C diode, right? So if you picture the 3 phases, we're going to get the positive of A, the positive of B, the positive of C, and we're going to send them through the diodes this way, and you're going to always have positive coming out right here, right? Can negative go out through there? No, it doesn't work that way. The negative is really going to ground, right? So we've got 3 positive diodes, 3 negative diodes. Why do you think the negative diodes have to be there? Think about it. What if those weren't there and we had A putting out positive? If A put out positive right here, wouldn't that positive just go ahead and short to ground? That'd be a direct short to ground. So we have to have a diode to prevent the positive from going directly to ground, to force it to go to positive, to the positive battery terminal. You know what I'm saying? Right? Same with B, same with C. So we have the 6 diodes arranged in this way. So that way, when the positive is generated, it goes to the battery. But when the negative is generated, it's blocked. It can't go to the battery. Cool. So it no longer produces AC. AC would be positive, negative, positive, negative. Instead, it's positive, nothing, positive, nothing, positive. So boom, now you got DC. That's its whole job. Now, what I was saying is, what if one of these diodes fails? Think about that. What if diode A failed? We would have positive being generated depending on the exact location of the rotor, right? We'd have positive generated and it would go to the battery. But then when the south pole comes up, wouldn't that generate negative? So we're okay with sending negative to the positive battery terminal? No. That would be AC. So if you had a bad diode, you would get positive and negative that would be alternating current. That's going to give you some issues. Like I was saying with electronics, electronics is all DC. If you have AC, that's going to cause some things. How do we test it? We're actually going to hook up a charging system tester, generally is what we would do. You could technically use your meter, your DMM, your Fluke or whatever, and you could test for AC voltage. And if you've got AC voltage, how's the AC voltage getting there? Well, this diode must be bad. It must be doing positive and negative. There's back and forth happening. If there's back and forth happening, that tells you that diode is shorted and it's allowing positive and negative. Kind of makes sense? If a diode shorts, yes. Diodes can actually short where it'll allow both ways, right? So a diode fails mainly in two ways. If it functions in this picture, right? I'm gonna go right here. In this picture, electrons go like this. If the diode is open, it's open. No electrons go anywhere. That's one failure. However, if a diode is shorted, electrons go this way and they go that way. That would be diode ripple. That would be a shorted diode, right? Would it be, is it how the diode's supposed to work? No, but that's the thing. The diode failed. The diode's shorted internally. It's allowing it to go both ways. So when you guys did the diode check on your meter, if you had an open diode, there's never any continuity. If you had a shorted diode, it would pass both directions, right? So you're supposed to do this direction and pass and this direction and fail. If it's shorted, it'll fail both. It'll pass both ways, which is a failure of the diode. Kind of makes sense, sort of? So now you guys can visualize how it rectifies it. Takes the three-phase, stands it up through that set of 6 diodes. That's your diode rectifier bridge right there. Right, and so this is just kind of saying each time the rotor rotates, the field changes from north to south, south to north, north to south, south to north. So the polarity of the phase winding reverses and the current changes direction. That's what happens in here. It's going to go this way. And then when this rotates another 180 degrees, it's going to go this way, right? And that's just the natural way that the alternator is going to work, because this north and this south is going to interact with that stator coil. Okay. And we could do it a few different ways, but if you're following so far, let's say each of these phases, you're going to notice A, then it's going to go B, then it's going to go C, right? And that's how you get A, that's how you get B, that's how you get C. Now do you understand why they're 120? Because if you look at this, if this is 0 degrees, 120 degrees later, 120 degrees later, it's physically laid out 120 degrees apart, right? You can see this is a full circle would be 360, right? And it's split 3 ways, so therefore 120. That's why they say 1/3. So that's 3-phase AC. If you wanted to do 4-phase or 6-phase, you could do kind of whatever you wanted, but 3-phase tends to give us what we really want, because if you look, if you only had 2 phases, you'd still have a pretty big gap. With 3 phases, you pretty much have something well into the positive at all times, so we really just needed 3. Right? And then, this is just walking you through it. The alternator itself produces these 3 phases. You notice anything below this line is negative, right? So if I were to pull this over, let me click this. Anything down here is negative. Anything up here is positive. So what could we do? Well, if this is 3-phase starting right here, we're going to send the 3-phase, and then after this point, all the negative is cut off. You notice that? So here's your positives. If you go peak to peak to peak, if you notice, there's a ripple right here. If you notice, that was a little squiggly. Your alternator is not dead smooth. It does have a little ripple. That's your ripple. If this ripple was too much, like let's say this ripple was like this, that would tell you, hey, there's a bad diode. Cool, and that's one of the tests that we'll do. All right, not really rocket science. You could test it with an oscilloscope. Yeah. I mean, this is exactly what you'd see if you did an oscilloscope. The cool thing is we don't really need to oscilloscope this because like ultimately we can trust that this is occurring because if we get this right here, if we get a nice ripple voltage at 13.6, we know that this is good. Now, if you get a reading that's like under 13.6, how do we know that one of these phases isn't bad? Imagine that this red phase was gone. You guys understand? Imagine if that red phase was gone. You just have blue and black. You'd have a big gap right here, right? If red was gone. If you had red gone, what would your ripple look like? If red was gone, you'd probably be way down here and then up here, and then way down here and then up here, and then way down here. There'd be too much ripple. You'd know like one of the phases is not working. It'd be way lower on average. Yeah. When you put your meter on there, your meter is really running an average, right? So if your voltage was, let's say in one moment it was 13.5, it'd be 13.5, 13.5, and then it'd be like 0. 13.5, 13.5, 0. Your meter is not likely going to be fast enough to catch this because remember, this is happening really fast. If we were talking about 60 hertz, that's 60 times per second. Your meter can't catch that. Now, an oscilloscope could actually. If you had one bad phase, an oscilloscope would show you. You could graph the 3 phases and see red is dead. Or even if you just monitored the voltage, you would see more of a waveform like what I drew right there. But if you're just using your meter, because your meter's seeing 13.5, 13.5, and then 0, it's not going to show 13.5. It's going to show more like maybe 9 or something, right? Now, you probably never read 9 because your battery is going to be 12-ish, so you'd probably be like 12. So what would that actually look like for you as the tech? You'd be like, the battery light is on. It's probably the alternator. Then you'd check the voltage with your meter, and it would most likely read like battery voltage, like 12.4, but it'd probably be going down, right? Because if you think about it, if you were to disconnect your battery and measure the actual output of the alternator, if it was 13.5, 13.50, and it's only producing 9 volts, you'd be like, oh, wow, this is only producing 9 volts. You'd know that the alternator is underperforming. It could be because one of these phases is dead. But keep in mind, it could also be this diode is open, right? And that can happen, especially because this makes a lot of heat. These components and circuits can fail. So if you had a bad diode, you're only really working off 2 phases. It's going to be a low output. I'd say the main reason it gets complicated is because there's no real way to measure one phase. You can only really measure the output of the alternator. And if the output of the alternator is low, you can therefore assume it's a problem with one of the phases. But at that point, it doesn't totally matter. It's like the alternator is not putting out what it should. You just need to make sure the alternator has everything it needs to work. Then where it gets really complicated is if your battery is connected and your alternator is only putting out 9 volts, you'll still read whatever the battery voltage is. Make sense? It's just that your alternator is not charging it because your alternator is only making 9 volts. 9 volts won't push into 12. So in a sense, you don't know exactly what the alternator voltage is. The good news is, what's this voltage fully charged? 12.6. When the engine starts, the alternator should put out much more than 12.6. It should be easily into the 13s, if not 14. So if you put your meter on here and it's 12.6, and then you start the car and it's still 12.6, what's that tell you? Is your alternator working? No, not if it didn't go up, right? How should it go? 12.6, start the car, 13.5. And you're like, oh, the reason it went from 12.6 to 13.5 is because the alternator is charging. How much? I don't exactly know, but enough where it's pulling the voltage off the base battery level of 12.6, right? Mhm.
Somewhere on an alternator.
You could.
Still staying with that.
Well, so here's what's weird. If you look at this, which is a good next photo, I just got to drop the pen. If we look at this, this is your positive terminal, right? This is this is where it gets a little bit tough to visualize. This positive terminal goes over here to this positive terminal, which guess what? That's your battery. So here's your positive and your negative. Don't make fun of my artwork. I need therapy. So if you measure right here and you figure this is just a wire, it's the same measurement as right here because it's just a wire, right? So anywhere that's positive is all going to be what we're going to call source voltage. So if it's key on, engine off, the source of the power is the battery. But if it's engine running, really kind of the source of the power is now more the alternator, because the alternator charges at a higher voltage. So that's really where the power is coming from, if that makes sense. So you want to check source voltage here or here. It doesn't matter. It's going to be the same. Technically, you could check it on a fuse. Technically, you could check it at a tail light if the tail lights are turned on. That wouldn't be a real good way to check it, right? But key on, engine off, 12.6. Engine running, whatever the alternator's putting out, 13 something. Seeing that a little bit funny, huh? So it is very tough to tell exactly what's going on with the alternator. But the good news is it doesn't really matter that much, because if your alternator is not putting out enough to get you into the 13s, you know it's an alternator problem. Essentially, all you really need to do is say, is this alternator getting everything it needs, right? So there's only two main things we're worried about. The big positive terminal, like we showed on that last picture. So this big positive terminal right here, that's going to go to the battery. How? I don't know. Sometimes they go through a fusible link. Sometimes it goes directly to the battery, and there's like a little fuse on the battery right there. Sometimes it leaves here and it goes to the fuse box, and there's like a big fuse in the fuse box. So if we had any open on that wire anywhere, that would cause the charging system to not work, right? Although in a kind of a weird way, it's because this is the source of power and we need it to make it out to those things. So if it goes from here to a fuse and the fuse is blown, guess what? The power from the alternator is never going to make it to the battery, so your source voltage is going to be low. What's really cool is one of the giveaways, if you were to check the battery and it were to read 12.6, but then you were to check this and it were to read 13.8, you'd be like, oh, it's on the positive terminal, because this is generating 13.8, but it's not making it to the battery. So you'd know to check this part of the circuit. That makes sense. I got a diagram I think will help that.
Well, the alternator's good.
Yeah, if the alternator is putting out 13.8, but the battery's at 12.6, the 13.8 is not making it to the battery. So it's somewhere in that big positive terminal. I'd probably go after the fuse. I'd probably look at like, where is this fused? Because it's fused somewhere, right? If you're kind of tracking so far, when we get into the diagrams, I think it'll help. And the ASE has some charging system diagrams. Right, so there you guys got a good shot of the drive belt. I think you pretty much understand that's where the mechanical movement comes from. And we know about the fan. This fan's built into the pulley. Sometimes, commonly, the fan may be pressed under the pulley inside the housing on the shaft, but just know, probably be a fan in there somewhere. Then when this alternator spins, it's, remember, similar to the motor, how we had that commutator, the alternator does something a little bit different, but the concept is still similar. We need to maintain contact with that spinning rotor. And so how can you maintain contact with something that's spinning? Well, we could use these things called slip rings, which is basically like a little contact. I got a picture of that. And we'll have a brush pressed up against it. So if the magnetic field is being induced into the, a spinning part, or whether it goes either way, whether the power is coming from the rotor or whether we're manipulating the magnetic field to the rotor, we need an electrical connection. We can do that through a slip ring that's going to spin around and around, and a brush is going to ride on it, so that way we can have an electrical connection. So if you imagine this spinning, how in the world could we can't run a wire to it, it'd be tangled up, right? Same with the motor. So we'll have those brushes riding against the surface. Those brushes can fail, of course, very similar to the motor. Here's like old school. Older vehicles, the rotor were supplied power by means of 3 diodes, the diode trio, a little older. This was called self-exciting. Because when the alternator would run, it would actually power the diodes and make its own excitation, which is kind of like fielding. Right. So in this style, we don't need anything from the ECM or the PCM. It's self-exciting. We can send it power on one wire, and those diodes themselves will be self-excited through the spinning of the alternator. It was simple, but you couldn't precisely control it. So that was fine on older cars. We didn't really care about fuel economy and emissions as much. So now, unfortunately, it's a little more complicated. If you were to go to the self-excitation, let's say that was this one, if you want to check the alternator, it's so easy. Literally, all you do, you'd obviously have the car running. You would go ahead and you'd check the output on the big terminal, which is right here on B. And let's say that the output was 12.4. That's probably actually battery voltage coming from the battery, making it to here at that point. You'd literally just go to the small wire, and you should have battery voltage there as well. That was it. It was like super easy. Or they even had ones that were more simple. You basically have the one big wire would power the diode trio inside, and then only one wire would come out, and that would go to your battery indicator. Right. So that was more self-contained. Basically, you check the one big wire, and if the big wire was good, and it didn't charge, your alternator was bad. It was that simple. There was no duty cycle. There was no ECM. There was none of that. It was also cool for hot rod stuff, because if you wanted to like custom do some engine and you're like, hey, I've got this alternator, all you really had to do is bolt this on and run power to it, and that was it. It would work. It would do its thing. It would probably overcharge, and it wasn't particularly efficient, but it was very simple because we didn't have to control those diodes externally or anything. Cool. Overall, pretty good. And then in other ones, like it says, initial current supplied to the rotor by the PCM. So that's more when we get into computer control. Here's the diode trio, by the way. Just 3 diodes in one. And this is still showing the sine wave, how we can rectify that. This, talking about the slip rings, I think I got a shot of slip rings. Let me skip forward just a bit. Here we go. Because we're talking about slip rings, understand if I want to field this rotor, right? So if I want to increase or decrease the magnetic field, look what I could do. I could make a connection right here. This wire would go to a brush. That brush would be pressed up against this slip ring. This slip ring is right next to this slip ring, but they're 2 separate circuits, right? So this would be a good way to get an electrical connection into these windings you can see right here. If that kind of makes sense. So if you think about it, as this is spinning, this brush is sliding across the surface. Eventually, what do you think is going to happen to the brush? Probably going to wear down, right? So like an alternator is, especially considering the brushes, this is a wear item, right? So when the car comes in for a no charge for the battery light on, my first thought is it's probably the alternator because an alternator is a wear item. However, if the car is 1 year old and it has low miles, I'm gonna be like, man, those brushes wouldn't be worn out yet, right? But if the car is 15 years old with 200,000 miles, I'm probably pretty comfortable with it being an alternator because we got these brushes that could be worn down and then of course those diodes have done a lot of work. So like it's pretty likely it's the alternator. But can we assume that? No, that won't hold up in court. You can be like, well, I thought it was the alternator because I thought it was. And be like, all right, well, what test did you do? And you're like, nothing. I just thought it was. Right. So that's not professional. Professional is going to be, let's measure and verify. Right. But this is a good shot of the slip rings and brushes. So now you can really see what we got going on right there. Now back up where I was supposed to be. And this is just talking about the slip rings, right? So a lot of words, but I think you'll understand, mostly now that you've seen the picture. So if we think about it, it's the circuit's completed through the slip rings and the rotor field winding through the voltage regulator to ground on the vehicle frame or body. So in this example, the circuit's going through the slip rings to the rotor field winding, which means if the rotor has a field winding in it, that means we can change the magnetism of the rotor because it's an electromagnet. And the stronger we make the magnet, what's going to happen? More output. Make sense? More output. And that's also going to make it harder to turn. So it's worse on the fuel economy and emissions side. Right. And so that's pretty much the purpose of those. So we have a connection there. Then if you look at, here's the stator. So if you picture the rotor, right, the rotor we had shown a couple times back here, that's the rotor that's spinning. We're going to make a connection to that through the slip ring and the brushes and change the magnetic field. Stronger is more output. Then on the stator goes around it and it's stationary. This is going to be the thing that we induce the current to, right? So if we send more electricity through the rotor, it's going to increase the magnetic field, and that's going to induce more electricity into this stator. So if this was a three-phase, we'd have three different sets of windings that are going to go to those 6 diodes. And each one of these is going to have its own little, like a power pulse in a way. So if you remember that magnet, how we had the north-south, we're going to have multiple magnets with multiple north-souths in that rotor. These are going to be the windings that were, if you remember the windings way back here, way back here, this will actually work. Here's these windings. Well, we're not just going to have, we're going to have one winding like this, but it's going to be at multiple points throughout the alternator. So this was just showing very simple 3, right? Electrically, there's 3, but mechanically, we're going to have this winding showing up in multiple spots spaced at 120. It's a little bit weird to explain, but that's why we have so many of these little, what we call segments, right? So this would be like phase 1, phase 2, phase 3, phase 1, phase 2, phase 3, phase 1, phase 2, phase 3. So not only are we having it hit 3 times, it's actually going to be even more often than that. But 1 is wired to, this is 1. Maybe I'll draw it like this. Let's make a 1 right here. That's 1. New color. Let's do this color. Let's make a 1, 2, 3, 1, 2, 3, 1. And this is 1, 3, 2, 1, 3, 2, 1. So we're going to have each one of the phases be reoccurring over and over. Why do you think we want to have that thing showing up so many times? It's the same reason we really have the 3 phases anyway. you're going to get a lot more generations of power through every revolution, right? So this is a way to increase the output. So if you think about it, if we had a bad phase one, this one wouldn't work, this one wouldn't work, this one wouldn't work, this one wouldn't work, this one wouldn't work. However, what would work? Well, what if we had two still working? Here's two. Here's two. Here's two. Right? So if you had one phase down, depending on exactly how, you could still have two. And then, of course, you guys know where we have nothing, you'd still have three. Right? So it's, you know, that's pretty much what's going on.
But it's still-
Exactly. So if one is open electrically, keep in mind, phase one looks like this, but this coil is going to be stretched out through all those different points. All those points, round and round and round. How many points in an alternator? I don't know. It depends on the design. Right? So if we think about how the newer cars need more and more power, we're going to probably have phase one. Electrically, it looks like this, but physically, this coil is very, very long, and it's going to show up, like we were saying, here, 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 here. If we wanted more and more and more and more power, we could actually probably have it, we could probably shorten these segments up and have it show up even more times, and then decrease the distance between the two, and then maybe even put a smaller pulley on this to spin that rotor even faster. So it's hitting more and more and more of those points because the RPM has increased. So we're coming up with creative ways to really generate a whole lot of electricity because the car has so much more electronics. We're powering all the computers now. You know, old cars had hydraulic power steering. New car has electronic power steering. So how are you going to power a whole new steering system? Alternator, alternator, alternator. Alternator is going to put out more and more power. And that's, you know, physically how it's going to look inside. But if one phase was out, you drop a third of the output. That's not, your electronic power steering is going to draw more than that. It's not going to be able to keep up. Cool. So it could be wired like this. It could be wired like this, delta. So Y spelled W-Y-E or delta. The difference here is kind of not really critical for us as technicians, but if you see on the diagram something that looks like this, that's your windings in your stator. Or if it's like this, that's your windings in your stator. If you see a diagram like this and you're like, what the heck is that? You'd be like, oh, cool. Look at that. That was what type of winding? Give you a clue. That's the Y, right? But if you saw one that was more of like a triangle, like this one, that'd be the delta, but kind of like, who cares really? But just so you know, those windings, remember, those windings need to go to the diode bridge, right? Because when that stator is turning, see, this doesn't show you the mechanical aspect, but it just shows you the electrical aspect. The stator is turning, or the rotor is turning, it's inducing current into, like, let's say this one in the Y, that's going to go to this diode. So if it was a positive produced, the positive will go out here, and look where the positive goes. In fact, we'll trace it. If you look at where the positive goes, we're doing a dyno test apparently. All right, so if we produce here, 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 if it's a positive, can the positive go this way? No, because it's blocked. Can the positive go this way? Yes, 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 yes. Look at that, 120 amp alternator fuse. It's going to go through there, and it's going to go all the way to the battery. That was kind of weird. Give me that right there. Okay, makes sense? Then, of course, if it's onto the B phase, it's going to do the same thing. So you see A, B, and C are all going to power the battery, but they're not going to be shorted to ground because this rectifier. And then when they're producing a negative, in a way, that's kind of how the negative will flow this way. Right? It's a little bit weird to explain, but when we're producing B, I should have drawn that in green. The negative flows this way. that winding becomes the load. And that's why we can have like, electrons flowing this way, like here. They can't just appear out of nowhere, right? So the negative's coming through this lower diode and leaving as a positive out through this upper diode and powering the battery, if you get what I'm saying. It does, and that part, if you see this letter IC, it's an integrated chip. So this is going to regulate something, and it didn't exactly show. So if I were to look at this, I can interpret this, which wasn't exactly what the slide's for, but it's a good question. Notice the ECM is giving some sort of signal. That's going to be our duty cycle, which will be a square wave like this. This up here would be on time. You want to do 50-50? There's half on, half off, half on, half off, half on, half off, half on, right? That's going to go to this regulator, and this regulator, if it's the one that I think, is going to control the amount of electrons go into this one, which is going to be, remember that rotor winding? This is going to have to go through the slip rings and brushes, and it's going to make the rotor more or less magnetic. And if it makes the rotor very magnetic, that's going to increase the amount of current that's induced into this field winding, which is going to go through the rectifier bridge, if that kind of makes sense. Was that a little too much for right now? Maybe kind of. All right, cool thing. This whole big box I just made in green, what is it? It says the generator, which is technically true. The alternator would be the AC side. It's alternating current. The generator generates DC. So if you look at this as an assembly now, it's kind of more like a generator. And the reason why is within itself, it's producing DC, right? So it's kind of weird. Sometimes we'll throw alternator or generator one way or the other way. In fact, in the time of AI, let's see what AI says. This will be, which AI do you guys use? I'm just going to do Google. Difference between generator and alternator. Let's see what Gemini says. Alternators spin a magnetic field inside stationary windings. Okay, to produce AC, which is then converted DC. Generators rotate armature windings within a fixed magnetic field to produce DC. And I guess that's the difference. So in that case, an alternator spins a magnetic field inside stationary winding to produce AC. So based on AI, I would actually say that generator is wrong. But that's what I'm saying. In manufacturers, we'll just throw alternator, generator, I don't know. But if you look, this is generating AC inside of a fixed winding. That's the definition of alternator. Generators rotate armature windings within a fixed magnetic field. Yeah, exactly. So I think that in reality, this is an alternator, but why do we call it a generator? Because it produces DC. At the end of the day, what's coming out is DC. But if I'm understanding it right, and Gemini didn't let me down, technically this is an alternator that's rectified truthfully. However, if it's rectified DC, it's easier just to call it a generator because we're measuring DC. We can't get in here and measure the AC, if that makes sense. It's kind of weird. If they say alternator, say alternator. If they say generator, say generator. If somebody asks you the difference, you can try to remember what I just said, but I'll probably forget it and be like, it doesn't really matter. A generator should produce DC just the way it's set up, whereas an alternator produces AC, but then we rectify it into DC. So like, is this a generator? It's kind of like, not really. It's kind of weird, huh? So, but now you guys can see the visual, right? There's some pretty good animations on this. If you picture phase one, negative coming up through the negative diode, going to positive because there's electricity induced, and going out through the positive and going to the alternator. And essentially, in a way, think of the three phases as like a three-cylinder. If you have a three-cylinder and it's only running on two, and let's say B doesn't work, obviously you're not going to generate as much amperage, but you're also not going to generate as much voltage overall. And that's an underperforming alternator. And if your alternator is underperforming, that's when you're going to get a lot of times this L terminal. If let's say we're under 13 volts, what's going to happen at L? Because this is a computer chip. So what I could tell you, if we were to look at like a logic gate or something, if it's got a ground right here, if it's under 13 volts, do you know what this integrated chip is going to do? If it's under 13 volts, it's going to send ground over here. If I send ground over here, look what happens. Look at that. Now, what's happened on the top side of this? This has got a fuse, so we know this is positive over here. If I've got a positive here and a negative here, do you know what happens? Of course you know what happens. This light's going to light up. What is that light? That's your battery light. Bless you. Why is the battery light? It's a charge indicator, really, but if it's a battery light in this discussion, why is the battery light on? Exactly. So now let's just say we change it, and let's just say you start the car and now the alternator starts working. You know what's going to happen? It's not going to send ground over here, which means there's going to be no ground here. There would, however, still technically be positive because the positive's there all the time. Right, but this charge indicator won't work because the alternator hasn't given it ground, right? So what's kind of weird, when you first turn the key on, this gets ground. Then when you start it and it goes above 13 something, it takes the ground away. What's that cause the light to do if it takes the ground away? Bingo, that's what you should be checking for. When you jump in the car, you do key on, you see the battery light, you start the car. If the light turns off, you already know that the alternator's working because it came above 13 something. Makes sense? And it turned the light off. Cool. So that's really how the system works precisely. All right. So what about, we got a couple of diagrams to diagnose here. If we had high output voltage. All right. So let's just say the regulator sensed voltage was above 14.5, right? If you see this regulator, they don't show us the electronics, but if the regulator senses above 14.5, what should it do? That's too high, right? Do you think your light bulbs and your computers and your modules of various types are happy? They like 13 something, maybe 14.1, not 14.5. So what should it do? It should decrease, right? But how? This thing, whoops, I skipped one. This thing, no, that was right. Yeah, this was right. This thing is going to say, hey, the voltage is too high, right? The way that it knows, and this is one of the inputs we have to make sure it's there, is look at S. Okay. S terminal comes from the battery. I'll change over to highlighter, so I'm doing it really how it's supposed to be. Comes from the battery, goes over here. When the S terminal, which is more like the sense terminal, senses, oh, the voltage is 14.5, it's going to be like, whoa, that's way too much. It's going to send less current to this thing, which is the stator electromagnet. So if we reduce the electromagnetism on the stator, right, that's the one that goes through the slip ring and the brushes. If we reduce that magnetic field, it's going to produce less induction, right? You remember the induction thing? So if it produces less induction in phase one, it's going to go up here like this. It's still going to go to positive, but it's going to be less current flow. So if we have less current, the battery, all the accessories running are going to kind of burn up that 14.5, and maybe this should drop it to maybe like a 13.7 or so, right? So this regulator really controls the magnetic field on that rotor electromagnet. Make sense? kind of. If it was 14.5 and that regulator chilled out the magnetic field a little bit, it wouldn't necessarily be super instant because the electricity is already produced, but everything that's consuming it is going to burn down that 14 something pretty quick. So it wouldn't be like 14.5, 13.7. It'd be like 14.5, 4, 3, 2, 1, 13.9, 13.8, 13.7. Probably a little faster than I could speak it. Right? That would show you, hey, this regulator is doing its thing and controlling it. Now, if this regulator were to have a failure, it could unintentionally overfield this. And sometimes they have different fail safes. So depending on the failure, it could overfield this, which would give you the 13.5, or it could give no magnetism, which will give you a no charge, right? If there's no magnetism on this rotor electromagnet, you won't get any charging. You'll get a no charge, which will give you just whatever the battery voltage is, in which case this light will come on, right? So actually, I'll tell you what, I got one for a no charge. Right here. Let's see. All right. So this one's an output voltage that's low. The windings in the stator generate a voltage and are sent to the charging current to the battery. So if we were to have, we could go two ways. Depending on what it sees on S, this regulator is going to say full field it if it's low. Like if your voltage is low, this is going to sense that on the S terminal, and it's going to make this magnetic field very strong and produce very high. Or if it's already too high, this is going to sense it, and it's going to reduce the magnetic field, which is going to reduce your alternator's output, right? So it's constantly changing. But let's say in this one, I got a pretty cool example right here. That would be good. Let's just say, for example, this wire was cut. If we had an open at this wire, what do you all think might happen? All right, let's say it goes one. I'll give you two examples, and it depends on the particular vehicle, right? If we have no S reading, let's say this is programmed. So when it doesn't have, let's say that the 12 volts comes off the battery, right? Let's do a highlight. 12 volts comes off. You have an open at X. What is the regulator seeing on the S terminal? Nothing. It's open. So let's say it's programmed. Yes. And a lot of times in a GM, this is called like the L terminal. A lot of times it'll set a code for that, by the way. Let's say, for example, it's programmed so that when it sees nothing, it knows there's something wrong and it defaults to maximum. It could default to maximum and it will literally field this magnet really strong. And when it fields this magnet super strong, it's going to put out maximum, right? When it puts out maximum, we're going to have ground coming through. Let's go with this one. Ground coming through, positive coming out, but it's going to be at absolute maximum output. This will max out. You could get like potentially 16 volts. Would this light be on at that point if you're putting out 16 volts? The answer would be no. It may set a code, and that's what's interesting. If you had a failure on this wire and it's programmed to put out max, you get an overcharge because it thinks that your system voltage is 0. So if your battery's very dead, don't you think it's going to maximum charge the car? Right? So it really needs this wire, the S terminal, to tell it what the voltage is. Now, let's say it's programmed the other way. Well, it depends on the system because this one's computer controlled. A lot of times the ECM is going to monitor this S terminal, and it might actually like give a check engine light and set a code. I can't remember the exact DTC, but it can, but not every car is the same. So I've seen some where you'll get an actual code set for the generator L terminal. But let's just say it's more basic than that, which this one is. This is a little bit more of an older model. Nothing. Now you'll just be driving and you'll be like, man, my battery smells kind of sulfury. Everything seems like it's bright and working. It could actually, if it's programmed in that way, it'll actually overcharge and you'll damage your battery and potentially burn out light bulbs. So there's sometimes an ASE question saying, light bulbs have been replaced and replaced and replaced. And the concept is if the alternator is overcharging, those light bulbs are going to fail sooner because you're running 16 volts. It's true. Generally, they're not programmed that way. So let's say it's programmed the other way. If it sees nothing on S, it may actually default to like, hey, we don't have anything on S, don't charge. So in which case it won't magnetize this, in which case it won't generate much. And there'll be like basically nothing going back to the battery. Your voltage will then be battery voltage, 12.6. But as your components, your lights and computers and ignition is drawing the battery down, it's going to be 12.5, 12.4, 12.3, right? What happens to that car? Eventually the battery dies. The whole time, what about this light? Yeah, this would be on, right? Exactly. So this would be a good example of a vehicle where, hey, this has all the symptoms of a bad alternator, but if you don't check to make sure that this S terminal is getting source voltage and there's a broken wire right here, you're going to replace an alternator and that's not the cause, right? So the main takeaway from that would be you look at this alternator, what does it need? Oh, here the L terminal is actually the light in this case. It does have an L. So this L terminal just does the light. Ignition actually powers it on. So if you had an open in the ignition, that actually wouldn't power up the regulator. It's not going to charge. If you had an open in the S terminal, depending on the design, it may charge at full or it may not charge. I don't know which one. It depends on the car, right? But if you have to check for battery voltage here, check for battery voltage here. What about on B? What is B? That's the big terminal. So you want to be tripped out? What if you walked up to the car and you just did key on, engine off, and you had 12 volts right here, but you had 0 volts down here? What's that tell you? Well, if it's key on, engine off, the power would be coming from the battery and it should go through the alternator fuse and it should make it to here and it should make it to here, right? So if you did available voltage, this should have the exact same as the battery, right? Let's just say this fuse was blown. In fact, that was my last page. Let's say this fuse is blown. I think it's actually the next page. If this fuse was blown, all this stuff could work. It might even field that coil, but then if you look, the power is going to try to come through and it's going to go to here, and that's the end of it. It's not going to make it to the battery. So what I was saying on the last one is if we did key on, engine off, you would most likely have let's say we have 12.6 coming off the battery. Let's say it has a blown fuse. How about that? We would have 12.6 right here. What would I have right here? If it's key on, engine off, you're probably going to have 0. You have nothing. That makes sense? Now, once we start the car, remember the power comes through here. So then what's really crazy is if we start the car, you're probably going to have at this one, what you want the alternator to charge at. About 13.5. What if you had a 13.5 on this side of the fuse and you had a 12.6 on this side of the fuse? How could that be? That's a weird number, right? The reason why is because your alternator is the source of power and your battery is the source of power, but they have no connection, so they're isolated. You have 12.6 in the battery, but you have 13.5 coming to the alternator. If this fuse was good, 13.5 would make it all the way through, right? Because 13.5 is higher voltage, so it's going to push to the battery. That one's kind of crazy. So typically the way we test the big battery terminal, because this is a big wire, we normally voltage drop it. Checking available voltage is kind of weird because it gives you some weird numbers. It's very confusing. So what we normally do, if you're running the car, you put your red lead on the most positive, which is the alternator B. And you put your black lead down here on the battery positive. And what do you think our voltage drop should be on this wire and fuse? Yeah. If it's like very low. Yeah, like how about we give it like a 0.2? If we have a 0.2 volt, 0.1 would be even better. If we have a 0.2 volts, we know that the cable's good, right? So normally when we want to test the big cable, we'll voltage drop it. Checking available voltage is good, except now you have two power sources. You have the alternator as a power source and the battery as a power source. And you're like, what's going on? Just voltage drop the cable. That'd be more normal. Now, the way that this diagram was supposed to be was what if we had an open right here? That's what gets really weird. Your battery 12.6 would make it all the way to this point, and your alternator may be charging at 13 something, but there's no connection there. So if you have no connection to here, if you think about it, this is 12.6, which means 12.6 goes over here, which means the voltage regulator is saying, hey, we have 12.6. That's not high enough, right? So it's going to send ground. It's going to make the light come on. So the light comes on. Should we put an alternator in this car? No. It could literally be an open at the big B wire, right? So if you were to simplify this to the bare minimum, in this particular type, all you need to do is find out what each of these terminals should have. So if I were to look at this, this should have 12.6. The S terminal, if I trace it coming for the fuse, this should have 12.6. It should have whatever source voltage is. Ignition, well, this comes from power, so this should have 12.6, right? What should be on M, though, and this is the first time we're really going to discuss the computer-controlled one. This is a unique diagram because it has the ability to be a mechanically controlled alternator with just voltages, or the ability to be computer-controlled. So if M is the electronic control, what do you think we should have on that wire? Give you a clue, it's duty cycle. Do you remember that? If you want to measure duty cycle, it's going to be a form like this. Let's say we did 10 on, 90 off. 10 on, 90 off. That would mean like it's only charging a little bit. That would mean the voltage is probably pretty high. We have to actually look for this signal on the B terminal. Make sense? So once you get into computer controlled, you can try to use your meter, but if you use your meter, you're going to get some weird number. If you have a meter that can measure duty cycle, do you know what this would show up on your meter as? This is going to be wild. What did I say this ratio was? 10 on. Yeah, so you know what your meter would read? 10%. So if you hooked your meter up and you put your black lead on negative and you put your red lead on B and you put it on duty cycle and it read 10%, what's that tell you? The ECM's given a good signal. So if the ECM's given a good signal and it's not charging, that's your indication. Or let's say I were to switch it and I were to make it more like 90 on, 10 off, okay? What if it was 90 on, 10 off? What should I get on this terminal? Exactly. So if you have a way to verify that the ECM, whoops, I pointed to the wrong one. If you have a way to verify that the ECM is giving the correct duty cycle, your diagnosis is done. See, so before computer controlled, you're just measuring for 12 volts in ground where there's supposed to be 12 volts in ground, which by the way, we'd also want to verify this ground right here, right? We don't necessarily need to verify the L because the L doesn't control it. If we had a battery light on and we checked the voltage and the voltage was 13.5 and the battery light was on, then I'm worried about L because L is just for the light. Cool? Go ahead, shoot it.
But that's a fuse. We've seen that like single looking fuse.
Yeah, this is a fusible link or like a maxi fuse because you don't have little fuses that are 120 amps. So sometimes it's a fusible link that's actually, built into the cable, or other times it goes to a big old fuse. This is not going to be a little, this is going to be a hefty fella. if I would say. Okay, kind of makes sense how you diagnose that. So if you take away anything, there's a lot of stuff going on the alternator. It's good to know, but maybe not always a need to know. However, what's absolutely a need to know is, does this alternator, is it getting everything that it's supposed to get to work? If it's not getting the B, it's not going to charge. If it's not getting the M, it's either going to overcharge or undercharge, probably not charge. If it's not getting the S, again, that's going to overcharge or undercharge depending on how it's programmed. If it's not getting the IG, it's not going to charge at all because it can't power up the regulator, right? So if I rolled up to the alternator like this, a lot of times what I'm doing is I'm just saying like, hey, I could voltage drop the big cable. I could just check the fuse too. Sometimes you can look at them. But really, I'm going to say like, am I getting good battery voltage here? Key on, engine off. That's going to kind of tell me, or maybe better to do the drop. Then I'm going to go to the smaller terminals and say like, hey, what are you supposed to have? What are you supposed to have? What are you supposed to have? And really with like in this picture with like, let's see, 1, 2, 3, 4, with 4 measurements, you can confirm, does the alternator have everything it needs to work? If it's missing one of those 4, what should I do? Figure out why it's missing. If it's missing the S terminal voltage, figure out why it's missing the S terminal voltage. That's actual diagnosis. Yeah, exactly. If you don't have 12 volts here, maybe back up to this connector and see if you have 12 volts here. Maybe back up to this and see if you have 12. What if you have 0 volts, 0 volts, 0 volts, but you have 12 going into the fuse and 0 coming out of the fuse? It could literally be a fuse and you could throw a $300, $400, $500 alternator at the car. See what I'm saying? That's like your need to know. Your need to know is whatever this thing needs, it needs. And if it doesn't have it, figure out why it doesn't have it. M is going to be a little tricky. I think I might have pulled an oscilloscope picture over, so that would be good. I think now you guys could understand like this can be shown in different diagrams depending on the manufacturer. But if you look, this is going to be more of the same, right? Battery positive comes in. This is going to be connected through the slip rings and brushes. So this regulator is going to control the field coil for the rotor. And then this going in close proximity to these windings is going to generate electricity, which is going to go through the rectifier diodes. This looks like this is the diode trio apparently. So that's interesting, right? So, and if we have, over 12.6, it's going to turn this light off because it's kind of weird. If you look, positive to positive would turn the light off. But if you don't have it enough positive over here, this is going to be ground. It's going to turn the light on, right? So it can be wired a bunch of ways, but the criticals are understanding the regulator controls that field coil to increase the magnetism or decrease the magnetism, which is then going to induce it on these rectifier bridge diodes, which is then going to make sure that only positive comes through and only positive goes to the battery, right? That's the gist of it. Wired with a Y, wired with a delta, whatever, that's all not important. Here's another example of a rectifier. So this is going to rectify. I wouldn't be surprised if the regulator's in there somewhere too. There's a pulley in the fan. And that's just the point of that. There's the overrunning clutch, because I do want to get to where we check that duty cycle. I know I got some for that. Remember the overrunning clutch, improving operating smoothness, decreasing belt slippage. Remember, especially when we shut it off and it kicks back really fast, it can make the belt slip, could decrease some noise. It's also better for the alternator to not turn backwards every shutdown, so it's going to increase the length. All right, and so we talked about how to access this. So if we're looking at this one, sometimes it's just a visual. This is your big B. That's the big battery terminal. Do you see this little connector right here? That's all those other things. the ignition, the ECM controlled the duty cycle thing, anything relating to the magnetic field. What do we call it? It was the S, I think, on that diagram, right? So there's a big connector and a small one. And so if I were to jump back to here, you'd know this is the big wire. It's all by itself. All these M, S, I, G, and L, those are all going to be on the small wire, right? So like on this one, there's just one small connector right here with 4 terminals on it. So all those other things are on this one. Which position? I don't know. That's when we go back to wire diagrams and we'd say like, maybe this is terminal 1, 2, 3, and 4. If I want to check M, I need to find terminal 1 in the connector and actually back probe it, which is actually some of what we're going to be doing next week too. Although for lightings, right? So that's what that was really saying. You just can't see it that well because a lot of times it's covered by a rubber boot, and that's to protect it and for heat. We talked a little bit about the battery.
So for our lab, we're gonna focus on.
Yeah, and let's see what we got for different types, and let's take some measurements on the smaller ones too. And I'll even make sure we find a computer controlled one, and let's check that duty cycle. So this will just summarize. If we have a problem with an alternator, we generally replace the unit, right? If it's a noise, if it's a no charge, if we verify all those wires are giving what they're supposed to give, we don't necessarily care if it's the regulator, the rectifier diodes, or the field coil winding in the rotor, or we're just going to do an assembly. Okay, so everybody understands. Stethoscope would be good for noise. If we really are, trying to diagnose a noise, the stethoscope is helpful, but a lot of times you can use a screwdriver too. If you touch the alternator, put it up to your ear, you could usually tell if it's the alternator. Literally put the screwdriver to your ear, like this, and just touch it to things. And the noise will transfer through the metal and right to your ear, and you can tell if something's making noise. It's the same as a stethoscope. It's just, you look a little more silly, which I like it. Even checking belt tension, without hijacking it. If the belt is loose, the alternator is not going to charge that well, right? Because the belt's slipping, be logical. Here is a good example of checking alternator output. So let's say that your alternator should put out 100 amps at 2000 RPM. This is how we do it. Inductive amp clamp, measuring the output of the alternator. That's on the big terminal, the big B. But at the same time, it'd be a good idea to monitor the battery voltage. And if you look at this number, the more amps that are going through here, the higher this battery voltage number will go because they correlate. The more amps your alternator puts out, the higher it's going to charge the battery. Right? And then what we should do is we should turn on a bunch of electrical loads, blower motor, windows, lights, these types of things. The more electrical loads we have on, the more electrons are leaving the battery, even the defogger. This amperage should go up. So if you're at idle, or even if you're at 2000 RPMs with like no lights on, you might have 10 amps going through. But if you put on a bunch of electrical loads, it should rise up to meet all the electrical loads at any time. And then if we continue to do that, if the alternator is keeping up, what should the battery voltage do? Should stay pretty high, right? But if your alternator is not able to put out as many amps, let's say because of the diagram we saw, maybe one of the 3 phases is dead, you might start to turn on your defogger and your wipers and your lights and whatever, and your alternator may not be able to put out enough amps. Your battery voltage is going to start falling. If your battery voltage starts to fall down, you're kind of like, hey, I don't know if this alternator is good. Keep all that stuff running and see, maybe it'll stabilize around 13.8 or something, then that'd be fine. Or 13.5 could be fine. But if it keeps going down, 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 that means your battery is in a state of discharge. If you keep doing that, you're going to draw the battery down and the car will die. It'll die on the side of the road, it'll be dead. And it won't restart because the battery's been drawn down. That would be a typical failed alternator. It can't keep up with the electrical demands, right? Make sense? So you can monitor the number of amps and also watch the battery voltage. They kind of go together. I like to watch both. Sadly, though, that means you need two tools. So go ahead. It's all right. That was only for this particular example. So a lot of times what we do, if we have a nice inductive clamp, the reading will be on the clamp. But for the Fluke, they have an adapter that goes into here. It's like attenuator where 30 amps will come up to 30 millivolts on the meter. 10 amps on the inductive clamp will come up as 10 millivolts on the meter. So that was a Fluke specific example. It depends on your exact meter and your exact device, but however you need to determine the amps, just keep in mind you'll probably have pretty low amps with no electrical load, and you'll probably have pretty high amps with a high electrical load. Well, in this case, it's going to be in millivolts. It's kind of weird, but this device takes inductive measurements. And if you have 30 amps flowing through here, it converts it to 30 millivolts, which plugs into your meter, and your meter will read it in millivolts. Your meter is showing millivolts, but that's because this device changes amps to millivolts. So you'd have to know, like on this clamp right here, it'll say something like one amp equals 1 millivolt. So if you know 1 amp equals 1 millivolt and you've got a reading of 30 millivolts, how many amps is it really reading? That'd be 30 amps. Make sense? That's it. I don't know. It depends on what we have. Everybody's got something different. So this is an example of, you just really need to know you need to know your specific meter. So if we had an inductive clamp, I'm actually going to pull, let's say on Amazon. Okay. We'll do like an Amazon inductive clamp, because I don't know what's the most common right now. Let's go with Amazon.com. Let's do an inductive amp clamp. All right. This one's going to read in amps right on the screen. This one's going to read in amps right on the screen. This one has no screen. This one is going to plug into your meter, and it's going to give you some conversion factor. 1 amp equals 1 millivolt or something, right? So which one you use depends. I don't actually remember which ones we have. This one reads on the screen. This one reads on the screen. Most of these are reading on the screen. This one's not, right? So if I look at this one, you notice there's no numbers. So we can set it like this. And then I wouldn't be surprised if somewhere in the pictures, it's going to show the calculation of, 1 millivolt equals 1 amp or something. So good question, but it really depends on exactly the detail, which I can't say. But short of just, being familiar with the meter, the concepts will still be the same. All right, but there's still a little bit more. So let's say we go to test the alternator. You want to test the voltage drop on the positive term, the B cable, the big cable. Your red lead goes on B, your black lead goes on the positive terminal of the battery, and it should be less than 0.2. Does that sound familiar? That is the voltage drop of the cable. We should test the voltage drop of the cable when it's running, when it's charging, under the most possible stress to potentially point out any minor error, any faults. Make sense? The more amps that flow, the more hot things get, and the more you're testing them dynamically. So this would be a good charging system voltage drop test. But we should also test the ground side. Our black lead should be on the negative terminal, and our red lead should be on the case of the alternator, because your alternator is grounded through the bolts. So if you had a nice powder coated cool alternator and it didn't have a good connection through the paint, that could be a voltage drop, which could be an undercharge condition, if that makes sense. Right? Checking the one-way clutch. It's just freewheel one way and lock one way. That's a real easy check. And then talk briefly about why hybrid and EV is different. Remember, there is no, like I mentioned in the beginning, there is no alternator. There's a DC to DC converter. So you're looking for this, you're not going to find it. There's just literally a section in the vehicle's inverter that takes your high voltage battery, 240 volts, regulates it, and gives it to the auxiliary battery at, what do you want an alternator to do? 13.5? Fine. The DC-DC converter will give 13.5. There's no spinning. There's no noise. There's no belt. There's no separate component. It's a little section built into the actual big battery inverter. So it's kind of interesting. And so that's what we're talking about with the DC-DC converter. So just be loosely aware that DC to DC converter charges the battery in a hybrid vehicle without moving stuff. Makes sense? It's all solid state. Cool. So if we look at that, here's your DC-DC. We got big battery voltage coming in. It's got its electronics, and you're going to have 13.5 volts come out and go to the battery, keep it charged all the time. So it's pretty neat. This would be the big wire coming from the battery, go into our inverter. The wires that go from the inverter to the battery are not going to be orange because they're not high voltage. Makes sense? So all this is doing is taking your big high voltage DC and making it into a small DC to power the little 12 volt stuff and keep the battery charged. Right? That one's fairly simple. Cool. So what we're going to focus on are some of the measurements. This is going to prep you for what we're doing in the lab. So let's say we're going to do that voltage drop test. If you remember the diagram, this should make sense. We've got the red lead on the big battery terminal. We're checking from the big battery terminal, and the black lead is going to be on the positive battery, right? Just like that diagram a couple minutes ago. And right now we've got a 0.1 volt drop. What do you think? Is that good or bad? Let's see. We back up right to here. This test is what we did right here. Red lead on the big battery terminal to the alternator, and then black lead on the actual red battery terminal at the battery. And we got a point, what did we get, a 0.2, 0.1? 0.105. Is that a pass or a fail? That's a great pass. So your battery terminal is good all the way to the alternator. Very nice. And then this is measuring the ground side, right? If you notice, this is clipped onto the housing on the red, and your black lead is over there on the black terminal of the battery, the negative terminal. And we got a 0.02 pass or fail. 0.02 volts. I'll give you a clue. We don't want more than 0.1 volts. And this is 0.02. This is a very good pass. Oops, right here. Black lead is on the negative terminal of the battery. Red lead is on the case of the alternator, the housing, right? And in this picture, we can only show one. Be good to get two, right? If you look, that's on the housing, but you can't see where the black lead is. Just trust me, it's on the negative terminal. So that's your ground voltage drop, and the first one was your power voltage drop, right? Now, if you want to measure the amperage, we got to do an inductive amp clamp. You see which wire this is on? This is on the big wire. We're going to actually measure how many amps are coming out. Which way are the amps going to flow? If the battery's down here, the amps are actually going to flow out of the alternator into the battery. This a lot of times has an arrow on it. If you have it put on the wrong way, it's going to show your alternator's charging at negative amps. Alternators don't charge negative amps. Your clamp is flipped, so just flip the clamp. There can sometimes be a zeroing procedure on these clamps to make sure that they're reading calibrated proper numbers, so you know. Then here's old school machine. This is actually a nice one if you want to measure amps and volts, but it's way outdated. So we're not going to use this one. But remember how I was saying it's nice to use amps and volts? That means you need 2 meters, or if you have a specific battery starting charging system tester, you can watch the volts, right? It's at 14.3. And the amps are going to be around like 20. So that would be, that alternator's keeping up just fine. If you put a whole bunch of load on it and all of a sudden, let's say it were to drop and you're down at 12 and your alternator looks like it's trying to field like 80, it sounds like that alternator is not able to keep up. What we're actually doing on this tester right here, this is an old load tester. We can manually add a massive load on the battery and draw it down on purpose. This would be kind of a cruel test. We don't do these anymore. But if we were to manually load through carbon pile, it's going to max your alternator out. And we're seeing that alternator is making like 82 amps. That's pretty good. This would actually be a pass. But let's say that we weren't doing a load test and you saw your alternator drop off to 12, and let's say you were only making 40 amps, your alternator wouldn't be keeping up, right? So that would be when you kind of use like what you've learned and say like, is this a pass or a fail? I'm at 2000 RPMs. I got all my lights on and my battery voltage is dropping and it's now at 12. Your alternator is not keeping up. Cool. But we don't load test these like this anymore because it was very harsh. Then of course we got to worry about the ripple, right? So if we're concerned about ripple, you can go ahead, AC volt your meter, 2000 RPM. Just literally, you're going to act like you're measuring battery voltage right here, just like this, positive, negative, but on AC. And what should you get? Basically, no AC. If you have an AC reading more than a half a volt, which is the same as 500 millivolts, you got bad diode. You're going to be replacing that alternator. Or if you really wanted, you could probably do the rectifier bridge in case you care. Or in the case, maybe the alternator is hard to get or something. Cool. And this just gets into belts and goes a little too much in detail. But obviously, if you have damaged belt and cracked belt, some of that's maintenance. If the belt's really that bad where it's slipping, it could cause charging problems. So this is mostly visual, setting belt tension, looking for cracks. There's a small lesson on belts built into this, but I don't want to hijack it and make it be a belt lesson. So just be familiar. There's all these belt tests. One of my favorite being this spring-loaded tensioner. As the belt wears and wears and wears and stretches or whatever it does, sometimes there's marks on your factory tensioner to tell you when the belt is worn. This one, if you notice, looks like those lines are lined up. That looks like it's worn out to me, but it would depend on the exact manufacturer spec. It may say like maybe this line starts over here, and as it wears, it gets closer and closer and closer. And then once it's to this line, that means it's worn. So they use concepts like that. All right. So I think everybody understands. If you're undercharging, what are your numbers like? An undercharge. Well, we should be in the 13s at least, if not maybe 14s, right? So if you're undercharging, what type of number? 12. Do you think your battery is going to have a long life if it's constantly undercharged? Undercharging alternators kill batteries. Underperforming batteries put a little extra strain on alternators and it may or may not reduce their life. Hard to say. That's kind of the goal there. Then we talk about PCM controlled. I think I've got at least a diagram. So remember, when it's PCM controlled, we're fine tuning. It could be anywhere between 13.5 and 14.5, depending on the computer's programming, on what type of battery, etc. So if we have AGM batteries, those have a slightly different charging profile. If we have lead acid, those are different. If we have lithium ion, those are different. So if the ECM is programmed to know what type of battery it is, it can charge differently. Like lithium ion batteries like a higher voltage. AGMs, if I remember AGM, I think AGM doesn't like very high amps. So they might reduce the number of amps, but maybe, they'll do a fine tuning of the charging strategy, they'll call it. Cool. So the main problems, no charge, undercharge, or overcharge. I think you guys know the difference now. If you're going to work on the alternator, make sure you disconnect the negative battery terminal first, because when we go over here, this is a big battery cable. So if you're trying to loosen this and you touch big battery positive to any chassis ground, do you know what you're doing? You're now welding. And do you want to be welding? Not on the customer's car when we're trying to do an alternator. We don't want to be welding, right? So be ready for that. because that does happen. But avoid it by disconnecting the negative terminal. That's basically what I'm saying. Also, look what this says right here. And so this is, I know what happens in the backyards and in the parking lots of the auto parts stores. Alternator must not be operated with the battery disconnected or with the terminals at the back of the alternator disconnected. Let me explain where we're coming from here. In the parking lot of AutoZone, there you are. You're like, hey, I think this got a bad alternator. Well, here's how Grandpappy taught me how to do it. You just disconnect the negative terminal of the battery and you pull it off. And if it dies, it's a bad alternator. And if it keeps running, it's a different problem. You're like, what? Well, here's why technically that works. If your alternator is not putting out any power, your car could still run on a battery, right? The battery will power the stuff. But if you disconnect the battery, now the battery's out of the equation, right? Who's left to power all your ignition and your injectors and your computers? This guy. So if you disconnect the battery and the car dies, it's because the alternator's not putting anything out. All right, makes sense? That's the backyard trick. However, the reason we're saying not to do that, it's not a 1955 Chevy anymore. Like there's a whole bunch of computers. How would you feel if you had all your desktops and your video games and your Xbox and your PlayStation or whatever, and you just rolled over and ripped the plug out of the wall? Is that the way you're supposed to shut computers down? No, so that's a big voltage spike. It's a voltage crash, or, potentially if you disconnect the battery, the alternator might start to super high charge and stuff. That's very harsh. So can you get away with it? Yeah, sure. Have I seen it done? Many times. Do I personally do it? No. But I know you could get away with it sometimes, but when you're a DIY person, once in a while stuff goes wrong, you're like, well, that's why I'm not a professional. But if you're the professional, this is not how we test alternators. So if you want to test an alternator, you don't disconnect the battery and see if it dies. Even though I understand it can kind of work, I get it. So how should we test it? All those ways we showed in the previous slides. You can test the amount of amps, you can monitor the amount of volts, you can rev it to 2000 and see if it can keep up with all the accessories on. If you really want to do it lazy flat radio style, just literally look at the battery light. If the battery light is on and basically if the battery light's on, it's a problem with the charging system, actually. If the battery light flickers, and you put a lot of electrical loads on and the battery light tends to be on more when the electrical loads are on, it sounds like the alternator output may be kind of low, right? At that point, all you got to do is just make sure this alternator gets the things it's supposed to get. 4 wires right here, and sometimes less, and then usually just the big B you can do the voltage drop test on. That's the correct way. Cool. Not disconnecting. You know what I've also seen? If somebody wants to change a battery because the battery's bad, they'll leave it running and they'll disconnect the battery, take the battery out, and the car will be running and go back in. That's also not approved. So for a couple reasons, remember your battery is a buffer. Your battery is going to stabilize the voltage. Your alternator it's choppy. Remember the diode ripple? The output voltage is choppy. Computers don't want choppy, rough, bouncy voltage. They want that battery to stabilize it. This is going to be much safer if the battery's in the car, not if the car's running and all your computers are powered up, running raw off the alternator, and you're in there saying, hey, I need a new battery in the store. Makes sense? So you do what you want, but if and when something fails, don't say I didn't tell you so. All right, cool. So that's kind of what this is saying, how to do the alternator, just by photos. There's disconnecting the big wire. Sometimes pulling the alternator and prying can be a pain. One tip I'll give you, this right here where the alternator hinges sort of, every time they make an alternator, there could be slight difference, right? So it's very hard for them to make this a precise measurement where it bolts onto your bracket. So a lot of times they have some sort of sliding bushing or something. When you go to pull it off, it's tight. You might have to work it, wiggle it, and pull it off. When you go to put it back on, what I would do, I would press that bushing back into the housing so it slides on really nice. If you find yourself not fitting this and the temptation is bigger the hammer, better the job, I'm going to say probably not. I would not be banging on this. This is not a thing to be banging on. Remember, it's got those windings in the stator. This is kind of delicate. This isn't meant for hammers. So go ahead and push that bushing back however you can, sometimes with vice grips or whatever. But another way to do it, if you thread the bolt in, if you take it out, wiggle it out, you go to put it back in, thread the bolt in this way, thread it into that bushing. You can even smack, not the alternator, the bolt, understand, with a hammer, and that'll usually drive it back a bit. Make it so it slides on easy. It's just a little technique action right there. Cool. And there's some brackets. Of course, make sure you put the this terminal on and know that that nut right there, that has a torque spec. Any connector that carries a lot of amps is notorious for having a torque spec. So it's going to heat and cool and heat and cool. If it's loose, that'll become unwanted resistance. Resistance, when it's a lot of amps, makes a lot of heat. If this thing is arcing and sparking, it'll actually potentially catch on fire, burn the insulation, this type of thing. So when we put that on, torque spec, and the torque spec is not tights tight and too tights broke. Make sense? So like look it up and actually torque it. If you break this off, do you know where that terminal goes? It's in that rectifier bridge. So if you break it off, guess what you're going to get? Another new alternator, unless you want to change the rectifier bridge, right? So you can't be breaking that stud off, but you can't leave it loose either. You got to have it torqued to spec. Pretty simple, right? Put the belt on, no big deal. And basically by the time you're done with that, start it up, make sure that the battery light is off, and that's how you know it's working, right? The rest is fairly simple. And if you guys got any questions, now's the time. If not,